We had awesome Baby Yoda helping us all the way through rational functions. If you saw Baby Yoda on a video, you know that we were talking about rational functions. We have a new topic now, exponential functions. They're very exciting. They're really powerful. They're awesome functions. So we needed kind of an awesome mascot for exponential functions. And we have them. The March sisters, Little Women, Beth, Joe, Meg, Amy March, from the great movie this last winter, Little Women. Whenever you see them, you'll know we're talking about exponential functions. Hello. We're going to talk about section 6.1, which is, the topic is percentage change. And this is the beginning of a new chapter. So we're going to have some new big ideas. We'll start off with a question. Would you rather have either $100,000 per day for a month? Sounds like a good deal. Or I'll give you 1 penny on day 1 of that month, and then I'll give you 2 cents on day 2, and then on day 3 I'll give you 4 cents. Day 4 I'm going to give you 8 cents, and day 5 of the month I will give you 16 cents. And we'll keep going until day 30. And so you get to pick which of these deals you want to take. This looks like a pretty good deal because you've got $100,000 for 30 days. And that will get you $3 million. If you take this deal, well, by day 30, what are we at? I mean, this is starting out small and we double every day. By day 30, on day 30, you are going to get, what would you guess? $10,737,418. We don't see all the days in between, but by the time you get to day 30, your daily deposit has grown to this. And in fact, for the whole month, if you add it all up, all of these days, you would receive $15.49 million. Definitely want to take deal number 2. This first deal is an example of linear growth. And this second deal is an example of exponential growth. We've talked a lot about linear growth in this course, and here for the first time we're seeing exponential growth. The deal with linear growth is to get to the next term, the next day, you're just adding by some constant. So add a constant number each time. With exponential growth, let's see, to get from day 1 to day 2, and day 2 to day 3, day 3 to day 4, day 4 to day 5, we are not adding a constant number, but we are multiplying by a constant each time. And these are the defining characteristics of a linear growth model or a linear function, and an exponential growth model or an exponential function. And this is the new deal here. This is what we're going to be talking about for a little while is functions that grow by multiplying. To get to the next term, you're multiplying by a constant, and they're very powerful. Chances are you've seen exponential curves in the news. Before we give the general form of an exponential function, let's look at a couple more examples. So example, say we have a table where our inputs are 0, 1, 2, 3, 4, 5. And the outputs of this function are 80, 40, 20, 10, 5, 2.5. As our inputs increase by 1 each time, we can tell that this definitely isn't a linear function because our successive differences don't remain constant. And this is an exponential function. The only question is, can we figure out what we're multiplying by each time to get to the next term? It's exponential, and we multiply by some number to get to the next output value. Let's see, what do we multiply 80 by to get to 40? And it would be the same number from 40 to 20. We're multiplying by 1/2 each time. And that's okay. It's okay if it's still an exponential function, even if what you're multiplying by is less than 1. Okay, one more example here. So this time I'm going to describe an exponential function, and we're going to try to come up with the equation for it. So f of x triples with every 1 unit increase in x. Also, we know f of 0. It's a really good value to know with exponential functions. This is when our input is 0. What is the function? This is sometimes called the initial value. And it's a very key element of exponential functions. Also, we know that f of 0 equals 5. So find an equation for f of x. This is our job. Okay, so I can't read all these words and come up with the equation, but I can start creating a table and maybe start seeing some patterns. So that's where I'm going to start. I'm going to create a table. And of course, we know that if x is 0, the output is 5. That's given to us. The other clue we're given is that it triples with every 1 unit increase in x. So if we increase x by 1, the output triples. So this would have to be 15. Another 1 unit increase in x, and the output triples again. Another 1 unit increase in x, and this triples again. So let's see, 90, 135. We'll do it one more time. Another 1 unit increase in x, and this triples. Let's see, that'd be 270, 405. Okay, so I'm getting a feel for how this function behaves, and now I need to come up with an equation for it. I know that f of 1 equals f of 0 times 3, because to get to this point, I have to multiply the one before by 3. And this is 5 times 3. I know that f of 2 is just f of 1 times 3. F of 3 is f of 2 times 3. F of 4 is f of 3 times 3. Okay, so rolling back a little bit, f of 1 is really just f of 0 times 3, or 5 times 3. So this part of it is 5 times 3. That's what f of 1 was, times 3. That's f times 3 squared. And I'm not simplifying yet for a reason. F of 2, well, that's f of 1, which is this guy, times 3. So f of 2, no, I should say it like this. F of 2, I just found out was this, 5 times 3 squared. This is just the f of 2 part, and I'm multiplying f of 2 by 3. So this is 5 times 3 cubed. F of 4 is f of 3 times 3. Well, f of 3 is this guy. So f of 3, it turned out, was just 5 times 3 cubed. And then I still have this times 3. Okay, so if I want f of x, it seems like the pattern is I always have a 5 out front, and then I'm multiplying by 3 to some power, and that power is always what my input value is. And it turns out this is the formula for the function described. Okay, we still have the March sisters, and we're going to give a formal definition of exponential functions. An exponential function is a function of the form remember, linear functions were y equals mx plus b. Exponential functions are y equals a b to the x. And a is the initial value of the function. And then if b is greater than 1, okay, so this b can be either greater than 1 or less than 1. We only deal with it when it's positive, but it still can be like a number like 0.5, or it could be a number like 3.2. If b is greater than 1, the exponential function is growing, and so it will be called the growth factor. If b is less than 1, if it's something like 0.5, 0.82, 0.17, then it is the decay factor. And as x is as x is getting bigger, your exponential function is getting smaller. If b is greater than 1, your exponential function will generally look something like this. It's growing as x increases. If this number here, b, is between 0 and 1, your exponential function will look generally like this. It's shrinking, it's decaying in an exponential way as x gets bigger. Either way, the growth factor and the decay factor are sometimes referred to as change factors. So if you see that phrase, it just means it's talking about b, and it's either growing or decaying. For an exponential function, this change factor can be found by taking the ratio of successive outputs. So we'll find it this way a few times, but we're actually going to find a better way to always be able to come up with b. So we'll say for now, b equals one output over just the previous successive output. Okay, I want to take a second and compare linear functions and exponential functions. They get compared a lot because they're two very common ways to try to model data. And and if you have some data, you want to know, should I use a linear model or an exponential model? And they definitely have different ways of growing and different ways of behaving. So we want to compare and contrast them. So for a linear function, as x increases by 1, the difference of successive y values is constant. And in an exponential function, as x increases by 1, it's not the difference of successive y values that are constant anymore. But as we saw here with what the change factor is, it's the ratios of successive y values. So linear functions, if you go from one to the next term, you're adding a constant number. And the ratios of successive y values in an exponential function are what remains constant. All right, let's look at an example. So much theory, we got to talk about real examples. Okay, say that we have this data table. Input of 2, output 13. Input of 3, output of 20. And I tell you that this data table is part of a linear function. And I ask you to find the slope. Okay, that's not too bad. We know that slope is difference of the y values, 20 minus 13 over 3 minus 2. That's 7 over 1, or just 7. And then if I asked you to find f of 4, okay, if the slope is 7 and if I'm at 3 and the output is 20, I know that just moving 1 on the x values, moving 1 on the input axis, I would move up 7 on the output. That's what slope tells us. So f of 4 is 27. Okay, say that as another example, I have a table of values. Okay, so we're going to remember this was a linear function. Say that I had a table of values like this. Input 2, output 13, input 3, output 20. This time I tell you this is part of an exponential function. So slope doesn't matter to an exponential function. It's ratios of successive y values. And if I asked you to find f of 4, well, I know that to get from 13 to 20, I multiplied by some number, and to get to the output for an input of 4, I would multiply by that same number. It's the change factor when I'm dealing with an exponential function. So I just have to find that change factor, and that's like my magic ticket. That's the thing that will enable me to generate any output that I want. Okay, so this up here told me that the change factor would be this output over the previous output. This is it. It's not a particularly pretty number, but this is our change factor here. And so we'll use that. So that means that g of 4 has to equal the previous input value 3 times the change factor, which is, let's see, g of 3 is 20, and the change factor is 20/13. This is 400/13, or about 30.77. So when my input is 4, my output is 30.77. Okay, so let's go one further and let's find f of 5 for the linear function, and we're going to find, how did I do that? This shouldn't have been f, it's g. So sorry about that. This is definitely g of 4, because this is g. And then we're going to find g of 5. Okay, f of 5, my slope is 7, so to hop to the next output value, I'm just going to add 7 more. We have that constant difference. It's easy. Okay, now this is not quite so easy. We want to find g of 5, and I know it's g of 4 times my change factor. G of 4 was this, 30.77 about. My change factor is 20 over 13. And so this becomes about 47.3. So if my input to g is 5, my output is 47.3. So this guy, even though they kind of have this table that starts out with exact same values, knowing that one's a linear function, it's going to grow in a particular way. It's going to grow, like say this is 213 and 320. It's going to grow in a straight line like this. And this one, our exponential function, even though it might have the same points on the function, it's growing in a different way. It's growing in a curvy and then really quick way. It may have been slower than the linear function right around here, but it speeds up because this change factor, once you start multiplying successive input values by that, it grows a lot quicker than the linear function.